All right, 3 different topics to cover real quick on this subject matter. This one goes to the last part of the lab yesterday. The middle one is going to be a little bit longer, and then the last one will be hopefully pretty quick. But first one is just kind of the final answer of the thing yesterday. This is how the color code works on resistors. It goes black, brown, and then the next is Roy G. Biv. Red, orange, yellow, green, blue, and indigo and violet are just 1. Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8. And then, it goes, I think, actually just 1 more, just white. Each color represents a number. 0, 1, 2, 3, 4, 5, 6, 7. I screwed this up. Hold on. 1, 2, 3, 4, 5, 6, 7. No. What do I want? Oh, I missed gray. There it was. That's why. My apologies. Beep, 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 beep. What are you doing? Stop failing, Spainer. Try again. Nope. 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 Can I have it? Thank you. Yep. Gray is 8, and white is 9. Okay. And the way that the size is listed is dependent on, you can see it right here. Scroll this up. The first 3 bands of the resistor. Now we said resistor is just some material that is inside of there. They can vary their resistors, and they're meant to be ohmic, so we can use them to use Ohm's law, correctly predicting exactly how much current is in a particular thing. And the way it works is the first 3 letters are, it goes color times 10 to the color. Meaning, if I have, like in your particular case, orange, brown, that would be 33 times 10 to the first. Now, one thing I want to point out to you here is, and I don't know why they did it this way, this is not scientific notation. It's really darn close. It's not scientific notation because the decimal is 33 times 10 to the 10th. That makes that 330. Right? Where scientific notation would be 3.3 times 10 to the second. Yes? So the way they construct them are not scientific notation. So basically, if you look at the bands, okay, look at the bands, you're going to have first color, second color, third color. And again, those first colors are 1, 2, 3. So humor me real quick. If I said green, blue, yellow, what's the size of that resistor?
56 times 4.
So how much? How much? Yeah, I know. What is that?
560,000.
Yes, 560,000. Now, there is a third band on it. Usually it's over to the side. Sorry, a fourth band, rather. This one is known for tolerance. There's a bunch of different tolerances, but basically what you can do within that is just go, where's it at? Where's tolerance at? That is not usually how I see it usually done. Yeah, I guess, no, that is, no, it's right. It's right. I'm sorry. And the tolerance is usually, you see it over here, gold, silver, or nothing. So there actually is nothing in that particular case. And for those, gold is 5% tolerance, silver is 10% tolerance, and if you have nothing, that is 20% tolerance. Meaning that if you have nothing on it, that's kind of a crappy resistor because the actual resistance could be above that by 20% or below that by 20%. I think these guys are, yeah, so these are orange, orange, brown, gold, which means they're 330 within 5%. So keep in mind that means that they don't fully know that they are exactly 330. So when you measure 328, that probably is exactly what it is. It probably is 328. It is probably not you're making errors because you can usually make these measurements pretty darn accurately, but that's within the 5% tolerance because for what? 333, 33 is 10%, so half of that, 15, 16 and a half. You can be plus or minus 16 and a half, and this still falls within tolerance. Does that make sense? Okay. That's the first conversation done and done from that particular point. So if you see a resistor now, you should be able to correctly identify, put it there, cool. You should be able to correctly identify what the color of that particular, or what the size of that resistor is. Cool? Cool. Topic number 2. How the heck do batteries work? So this is a bigger conversation. Huh? It's not going to take like a ton of time, but it's one that's kind of deeper. For my chemistry people, this is a redox reaction. For my non-chemistry people, don't worry about what I just said. All right. I am also going to draw some big chemistry swaths here. This is certainly not perfect. There's other things going on. But for our purposes right now, it'll work. All right. So I'm going to describe a battery in a very general way, and then I'm going to prove that it works because on Monday, you guys are going to bring me in various fruits. Okay? What fruit would you like to bring me?
Mango.
I'm not saying anybody. If you're saying mango, you are bringing me a mango on Monday. Yes? Okay.
Do you want me to bring you a fruit before school? Okay.
Who else? Who's bringing me a fruit? What are you going to bring me?
Can I just scrounge up something?
Well, I want to know what it is so that we're not all scrounging the same thing.
Probably a pear.
Okay.
What are we
I
doing?
feel like you guys are like going like the weirdest fruits
like
first.
I have here.
Let's-
This is like
It's my
expensive.
fridge.
Alright, mangoes and pears are
Fancy.
expensive.
Goodness, guys, you guys are fancy fruits
Wait,
on.
do you want a plum?
Thank you. An apple would be great. What else?
Do you want a plum or a pear?
Yes, one of those.
Oh my goodness.
Plums, I like
Any others?
Yeah.
I did like 5. I want like 5 because some of you are gonna forget, and ideally we have.
Wait, can we bring like a tomato?
I've had somebody bring like a full pineapple before, then we split up the pineapple afterwards.
Banana.
I will be here.
Banana. Do a banana. Somebody, you're gonna bring. Well, you already did. You're doing an apple. Who's bringing a banana? You're gonna bring a banana.
Someone should bring it.
And I got one more. I got mango, pear, apple, banana. What?
Someone needs to bring an orange. I feel like it needs
Someone should bring an orange.
Someone should bring a kiwi.
What's wrong with you?
What's wrong with kiwis?
Nothing. You're picking some of the weirder
But
fruits.
they're
Blah blah blah.
small.
All right. So one more. Isaiah, Trent, Jaden. Trust myself. Put an alarm on your phone. Come on, it's not that hard to bring up fruit to school.
Literally, people can go
grapes.
down
Oh,
on
wait,
lunch
grapes.
time.
Fruit school on Monday.
They're gonna be fruit batteries.
You do whatever.
Small little compact.
Yeah, Gabe
Oh,
the
Gabe
peanut
would be
grape.
All right.
Okay, but it feels great.
Pick something at lunch that's not one of those 4. Moving on. So here's how it works. So imagine you have a liquid here that is fully connected, except in the middle is a semi-permeable membrane.
Oh.
Super fancy word, but essentially, in a nutshell, it lets through water and nothing else. In a nutshell, it's not perfect. Okay? So here's what we have to have. This liquid is known as an electrolyte. But what we specifically need to happen is I need to put a metal into the electrolyte. This should be bigger. That's bigger. I wasn't wrong. All right. So we're going to put a metal into an electrolyte that will then ionize. Okay? ions are going to come off it, meaning some charge something. So we'll call this random A. So coming off of this is ions, A plus ions. They're not great ions, they're just positive. All right. Next, we have some, this is very important, a different material over on the other side that will also ionize, but because it is different, the goal is that it ionizes either slower or faster. So for sake of argument, let's go ahead and say it is worse at it. These metals are known as electrodes. One of the reasons for the semi-permeable membrane is that those ions are then essentially not allowed to move through this particular medium in this case. Why are fruits ridiculously good at making batteries? They already have semi-permeable membranes built into them called cell walls. Some are better than others. But now, here's what happens. I told you that when we make a battery, that one side's positive and one side's negative. Actually, that's not entirely true. In this case, if positives come off, what's going to happen? No, positives come off a neutral thing, it's going to be negative, right? Okay? And if positives come off the other one, then, but less negative. So guess what we call that side? We call that the positive terminal. Is it actually positive?
No.
No, but if I connect it to a light bulb, that wire that I just connected the two parts of the electrode with has negatives in it, yes? Is there going to be a general push in a particular direction? Which way is the push? Left to right or right to left? Left to right, because there's more negative over here, and so it's going to push harder in that direction. There's going to be a net force in that direction on the negative. That being said, that direction would be the actual current. So what are we going to say is happening instead? It doesn't really matter, but we're going to say conventional current goes this way. Now, is that actually the way it goes? No, but who the heck cares? Because positive going left is the same thing as negative going right. And since there is a net force between these two sides, we would say, similar to a hill, that there is a potential difference between those two locations. For a standard AA, AAA, CD battery, that's 1.5 volts. That being said, just so you know, and people that are done redox reactions before will find that the maximum chemical reaction here is probably going to get maybe 2.8, 2.9. Your most stable ones are usually about 1.5. So if you actually open up a 9-volt battery, there's not a different chemical reaction there. It's probably the exact same chemical reaction. What you're going to notice is they are just stacked on top of each other. 8 of these stacked on top of each other, or 8 running at 1.5, is a 12-volt battery. I had one for a while. It corroded, so it might not be perfect. But interesting thing, when I can't remember when I did this. Oh, here it is. There's these batteries here. I've got a couple of them. Are they both corroded? Yeah, not bad. Not toxic. All right. So this little guy right here is you're probably not used to seeing this type of battery. This is like a camera battery. And if you buy one, you can buy one of these for about $1.50. And you ever try to buy like watch batteries or those like tall, small, tiny ones? Those can get really expensive really fast. Yes, you know what I'm talking about, like the watch batteries. Well, so it's a little bit annoying then that this costs $1.50, and if you look inside, there's 8 watch batteries literally just stacked on top of each other.
Can you pull them out?
Oh, 100%. You can pull them out and use them. Yeah. Now, Don't try to do this with every battery. I knew specifically that that was in there. I also took ridiculous precautions when opening that bad boy up because you don't want there's a chemical reaction all over the place if that's not what it looks like. But yeah, what's really frustrating is that like a pack of like 6 of these tiny batteries will probably run you about like $8-12 where this thing costs $1.50. And the answer, like, why is that? Why would they do that? Because it seems more expensive and you'll pay it. Is the answer. Well, at least those were the numbers when I originally did it. But yeah, so chemical reactions in this particular case. Now I will come back and talk about this conversation when we have another conversation in next chapter, chapter 18, on why something works particularly the way it is. But here it is in a nutshell. Take one metal, it ionizes. Second metal, it ionizes in a semi-permeable membrane, create a potential difference between the two of them. Now, why don't we use fruit? Why don't we use fruit to power stuff? Well, the answer is this. You can get a decent voltage out of this, but what you need is both voltage and current. Fruit does not do a good job of producing current because it does not run these ions off fast enough that you can get a current going through the system, which we'll talk more about a little bit later. But essentially, yeah, you can. There's a really good picture, actually. Where'd I put it? I think it's in my background. There's a really good picture of a gentleman who went to an orchard and actually hooked up. Hopefully he got permission first. But he hooked up basically as many apples as he possibly could to power one lamp. Let's see if I can find it. Oh no, okay. I think this is an artistic rendering of it. There's a different picture that does this, but essentially this is the gist. I understand.
Thank you.
There you go. This would not work. This would 100% not work. This is absolutely an artistic rendering of what it was. I'll try to find the real one, but the real one's a little bit less artsy fartsy. So there you go. All right. Questions, concerns on how you make a battery. So just to tell you, you're going to bring fruit in on Monday, and I'm going to show you that it 100% can power something that doesn't need a whole lot of current. But yeah, you're going to bring the fruit, so you're going to bring the semi-permeable membrane and the electrolyte. I will provide the electrodes in the form of a penny running on what material? What material would a penny provide? Copper, yeah, or at least the outside is anymore. And also a galvanized nail. And if you don't know already, or maybe some of you do, galvanized means zinc, essentially. So we have zinc on the other side. All right, one last topic that's going to be necessary for your lab, and then I'm all done. Okay, I don't know if this is going to translate super well onto the video, so I'm just going to tell you video people that if you want to see how to use a vernier caliper, ask me in person. Bye-bye.